Okay, guys, so today we're going to be covering the subgradient method. This is the second algorithm you're going to have learned in this course, the first being gradient descent, although I suspect gradient descent wasn't actually new for most of you, just probably some parts of the analysis or the perspectives. So the subgradient method is probably the most general or one of the most general methods we'll learn in this course. So it applies very broadly. You just need a convex function such that you can compute a subgradient at any point, which is typically kind of a weak assumption. In some sense, it looks similar in flavor to gradient descent. We just replace gradients by subgradients, but we're going to see it kind of has some different properties. So just to remind you of last time, we talked about unconstrained smooth convex minimization. So this problem where f is differentiable and convex. And we discussed and analyzed gradient descent, which just starts somewhere and repeatedly moves in the direction of the negative gradient. So that's what's being done here. And we saw that the step size is tk, so how far we move in the direction of the negative gradient. We could either choose them to be fixed and small. So our analysis said that if this gradient function was Lipschitz and we took each of these step sizes to be smaller than or equal to 1 over the Lipschitz constant, then that would converge and it would actually give us this rate, 1 over epsilon. Alternatively, we could use backtracking line search, which didn't require us to know anything about the function's curvature, like its Lipschitz constant, and had us just start with a big step size and basically reduce the step size until some condition was met, that condition being that we would make some fraction of as much progress as what the tangent line to our function would have made. Okay, so backtracking line search was a very useful thing to do in practice. It kind of chooses the right step sizes at every iteration, and that also gave us the same rate, 1 over epsilon. So we interpret this to mean if you want an epsilon suboptimal solution, then you need to take on the order of 1 over epsilon iterations. And so let's say epsilon is 0.01, let's say 0.001, so 10 to the minus 3. That's 10 to the minus 2, 0.001. Then we would take like about 100 iterations, okay, in order to get such an accuracy. So the upsides are all here, and the fact that it's also simple and typically very cheap and portable. It's not a complicated algorithm. The downsides are kind of twofold. The first is that it requires our function to be differentiable, and so that's something that we're going to be removing that assumption this lecture. And a second downside is that it can be slow to converge. That's something we'll kind of address throughout the semester with more and more sophisticated algorithms. But next lecture, at the very least, we'll talk about acceleration, which in some sense strictly improves on gradient descent. So we can just accelerate gradient descent to give it a faster convergence rate. So the subgradient method is, like I said, it's similar setup, except for we're not assuming that our function is differentiable. It's just convex. And it's like gradient descent, but replacing a gradient in every step with a subgradient. So we learned what subgradients were last time. In a word, they were something that gave us this property that we know is true of the gradient, that at any point we can construct a line that passes through the function value at that point that under approximates the function everywhere. So we know that g is a subgradient, just to remind you, of f at a point x means that if I were to build the tangent line through this point f of x having slope g, that it lies beneath our function everywhere. Okay, and the gradient does that for us if the function was differentiable. This is, say for convex f. So the subgradient method just requires us to find such a g. It need not be unique. Right? If it was unique, then the function would be differentiable at that point. But in general, it need not be unique, so we just take any one of them, any subgradient, and move in its direction, or in the opposite, in terms of we move in the direction negative g. Okay, so just notationally, this g superscript k minus 1 is a subgradient, or is in the subdifferential of f at the point xk minus 1, this current iterate. Something that's immediately apparent about the subgradient method, if you were to run this, pick your favorite, let's say pick your favorite convex function that's not smooth everywhere, is that you'll find that it's not necessarily a descent method. So what that means is that actually you can both decrease and increase the criterion as we move forward. And obviously we hope for, like decreasing the criterion net in the long run, but at any given iteration, we can actually be increasing the criterion. So it's not necessarily a descent method, and that's why I'm calling it the subgradient method. Although I'm sure, some percentage of the time I'll just forget and I'll call it subgradient descent. It's just kind of natural to call it that. But I'll try to avoid calling it subgradient descent because it's not really a descent method. So what we do is we keep track of the best iterate we've seen after k iterations in terms of the criterion value. So we just, let's say keep track of the lowest criterion value, and known that by, x best, f of x best superscript k. That's the lowest criterion value we've seen, and this x itself is the iterate that achieved that lowest criterion value. Right? So if you had to run it for 10,000 iterations, you would say that there was some iterate that was visited in the last 10,000 iterations that had the lowest criterion value, and you saved its identity. So if you were forced to quit, you would report that as your best guess at the solution. So today we'll talk about subgradient method, and oh yeah, question. That's a good question. So I'm not sure I could give you intuition for why that's true. That would be very convincing. So maybe we should just kind of clarify why we know gradient descent is a descent method. So at least as far as our analysis went in the last lecture, I guess this was something that we'll be proving on the homework. It came as part of the proof for gradient descent's convergence rate. But there was kind of the following fact, which is that if this is Lipschitz with constant L, then we used the fact that we could upper bound this by a quadratic. Okay. And then we plugged in the next step. So you plug this in. And we saw that if we took t to be smaller than or equal to 1 over L, then what we get is, from this quadratic inequality, that f of y is, or let's say f of x plus, is less than or equal to f of x minus t over 2 times the gradient of f of x squared. So this kind of logic was actually very similar to what we did at the end of the gradient descent lecture to talk about its conversions for non-convex functions. We just somehow didn't quite write it in this way, but this is essentially what we did. And this is what you'll do on the homework when you prove that under this condition for convex f you get a certain rate. So this is actually the proof of the fact that we descended every iteration. And it requires us to take a small enough step size. And we got it by actually invoking kind of a strong property on the function. And when we analyze subgradient method, which we'll do in this lecture, we don't have such an assumption. We don't have a gradient. We don't have really any control on any such upper bound control on the curvature. And that's not really an answer for, I guess, intuitively why it can happen. But maybe it's just helpful to clarify that we used kind of a stronger property to prove that for gradient descent than we have here. Okay, other questions? Okay, so we're going to see some differences, like this being one, for example, between how we view gradient descent and subgradient method. We'll talk about step sizes. I think we'll probably prove the convergence analysis for subgradient method, since I skipped the one for gradient descent and put on the homework for convex functions. And I'll talk about a few applications of the subgradient method, but one that's interesting is for an intersection of sets problems. And then at the end, I'll talk about projected subgradient method, which is what you could do if you had constraints. So one difference we see immediately between the subgradient method and gradient descent is in how we choose step sizes. So there are options for fixed step sizes in the subgradient method, just like we have with gradient descent. We could just set this to be equal to some kind of small step size. But we're going to see this is generally not a good idea if we're trying to optimize our function, because this is actually generally not going to give us a solution, even if I run this for arbitrarily long. So it is a choice, but it's not necessarily a choice that we think about, let's say in the classical applications of subgradient method really taking. The more common one is these diminishing step sizes. So we essentially want to choose step sizes that meet a pair of conditions. This is one such pair of conditions. It's not the only one. There are several other ones that you could look at, but this one I think is kind of simple. So we want the step sizes essentially to go to 0. That's what this is saying, but not too fast. That's what this is saying. So we want the sum of the squares of the step sizes to be finite across all the iterations, but not the sum of the step sizes themselves. Right? So this is saying don't go to 0 too fast. So what's an example of a sequence that meets these two conditions? Right? I just saw a hand and I heard a mumble, but I didn't. Yeah, 1 over k as an example. So this would be square summable but not summable. What is the sum of 1 over k squared, for those of you who remember? I heard a bunch of pi's. It's actually not important. I was just curious if people knew what it was. I think it's pi squared over 6, right? Okay, so we would typically take something like 1 over k. We could actually take 1 over root k. It wouldn't satisfy these conditions, but it satisfies another pair of sufficient conditions. There are other conditions essentially we could be looking at. And this one, I just think this one is an easy one to remember. Okay, so the difference between this and gradient descent, well, first of all, we didn't really think about taking step sizes like this for gradient descent. But moreover, we don't have something like backtracking for the subgradient method. We don't think about adaptively computing step sizes at given iterations. It's really something like this, or if we don't care about getting to the exact optimum, we'd choose a fixed step size, but we would not apply something like backtracking. So let's just jump right into the convergence analysis, because that's probably one of the more striking differences, aside from the step sizes, between gradient descent and the subgradient method. And we're going to, for this analysis, we're going to assume that our function is itself Lipschitz. So it doesn't have a gradient, okay, but it is Lipschitz itself, and it has Lipschitz constant g. Okay, this just simplifies the analysis. And one thing I actually wanted to point out, so if f is Lipschitz with constant g, let's say f is convex. So one thing you can prove from this that is implied by this condition is actually that if I take any, let's say g, that's in the subdifferential of f at any point x, it satisfies norm of g less than or equal to this constant g. So if you just look at this condition and you invoke Lipschitzness, you'll see that this is the case, that you can prove this is the case. So knowing that f is Lipschitz with a constant g, it tells us that the subgradients can't get too large in norm. So it is some notion of regularity on the function. It's just that we're not assuming that it's differentiable. This is kind of much weaker. Okay, so with this assumption, there's kind of a pair of theorems that we have for the subgradient method in terms of its convergence. The first is that for a fixed step size, so if I chose my favorite small fixed step size and I stuck with it, then what I get if I run the subgradient method for arbitrarily long, and look back at the best iterate that I've seen, I'm guaranteed that that's suboptimal by an amount g squared t over 2. Okay, and this is positive because this fixed step size here we're taking t is like something strictly positive. So with a fixed step size, all we can say is that we're suboptimal by a certain amount, g squared times t over 2. For diminishing step sizes, so that satisfy this condition, square summable but not summable, we actually know that if I run the method for arbitrarily long, then I approach the best criterion value. Okay, so both of these results are actually weaker than what we proved for gradient descent because we don't have, these are not like finite iteration bounds that at step k I'm this far from the optimum. And the proof is actually fairly different, so I thought we would go through it. But these are kind of the standard results for subgradient method. So here's the proof. The proof actually follows the derivation of this kind of basic inequality for what happens after k iterations. And then we can kind of read off both sets of results from that inequality. But let's say the architecture of the proof at a high level, what I described as the anatomy of a typical proof, is similar. Right? We start with some condition. We try to get some kind of sufficient descent out of that condition. And then we iterate, or we kind of recurse or aggregate across all the iterations, and we read off something about some global property. So what we can do with the subgradient method is really all we can do is use the definition of a subgradient. We've only assumed Lipschitzness, right? That's all we've assumed. And that's going to tell us that these subgradients aren't too large in norm. So we're going to have to essentially use that. And we don't have any other kind of condition. So we just look directly at, let's say, the squared distance between a point xk on the subgradient method path and this, like say, a solution x star. And we're just going to use the definition of that iterate. Right, it's just given by moving in the direction of the negative subgradient. And we're just going to expand this out, right, to try to relate this to what we had at the previous iteration, let's say. Again, similar in terms of the kind of high-level proof architecture. So I'm going to couple xk and minus 1 and x star because I want to know how well this is doing compared to the last iteration. And the other squared term is just tk squared times the norm of gk minus 1 squared. And that we know is less than capital G from our Lipschitz assumption. And the cross term is negative 2 times tk times gk minus 1 transpose xk minus 1 minus x star. Okay? So this is just comes, like I said, from just expressing xk as a function of the iterate that came before it and then expanding. So this thing, well, maybe, I mean, we'll bound this by g. I guess we can just do that right now. So this thing is less than or equal to tk squared times g squared. How about this thing, this term here? So this term we're actually going to use just the definition of a subgradient of g to bound this. Right? So I know that gk minus 1 is a subgradient of my function f at the point xk minus 1. So that tells me for any y, this holds. Right? This property holds. I'm just going to look in particular at y equals x star. You can guess that's the case because I have the subgradient inner product, a difference here between xk minus 1 and x star. So just the definition of a subgradient itself tells us that this is true. Right? This inequality, like I said, would be true for any y, but in particular it's going to be true for y equals x star. And, okay, in fact, this is just this. Right? I have a negative gk minus 1 transpose xk minus 1 minus x star. That's the same as this. I've just put a negative sign and flipped this. So they're the same. And I have a 2 times tk out in front, but that doesn't matter. And you can see that now I can just rearrange this to say that gk minus 1 transpose, let's say, x star minus xk minus 1 is less than or equal to f of xk minus 1 minus, sorry. Okay, I've just put this to the other side. Okay, so that I'm just going to basically apply this upper bound to this term. That's all I'm doing. And I'm going to get a difference of criterion values in place of this term times 2 times tk. Okay, so continuing on, we're just going to say that xk minus x star squared is less than or equal to xk minus 1 minus x star squared plus tk squared times g squared. And I'm going to write this as, let's say, minus 2 times tk times fxk minus 1 minus fx star. Okay, that's exactly what we had here. I just grouped the terms within the parentheses, and so I put the minus inside. Okay, and we're talking about the criterion values, right? I'm going to want to make a statement about how well subgradient method is doing in terms of criterion values. Eventually, that was what our theorems were saying. So what we can get by iterating this inequality So let's take maybe over all steps that go from, let's say the first step all the way through the kth. By which I mean I'm going to compare this, I'm going to produce the same upper bound on this, right? Analogously, at the k minus first iteration, this is upper bounded by the distance between xk minus 2 and x star squared plus tk minus 1 squared times g squared minus 2 tk minus 1 times the difference in criterion values. And I'm going to upper bound the appearance of xk minus 2 and x star in that by the same upper bound. So that's what I mean by iterate this inequality. Okay, we get xk minus x star squared is less than or equal to, well, we're going to go all the way to the first iteration, in which case we were comparing the initial point. And now I have the sum of tk squareds, I equals 1 to k, or I should say ti squareds times g squared. And here I'm going to have minus 2 times the sum of ti times f of x I minus 1 minus f of x star. Okay. So we're just going to maybe notationally call this thing R, just for simplicity, or R squared. This is just how far we were from a solution to begin with. It's just going to be a constant with respect to our analysis, so I'm just going to call it R squared for simplicity. Okay, and I'm going to just lower bound this by 0. So this is a distance. It has to be non-negative. Right, so just to summarize, this is what the bound looks like. Right, and the game is, of course, at the end to be able to say something about the distance between the best criterion value, or the gap between the best criterion value visited so far and the optimal criterion value. And so we can rearrange this, let's say, and just have the statement that just by moving this over to the left-hand side, 2 times the sum of ti's times f of xi minus 1 minus f of x star is less than or equal to r squared plus the sum of ti squared g squared. And this itself, right, this is where I'm going to use the fact that I only care about the best one so far. This itself is lower bounded by, let's say, 2 times the sum of the ti's times the best one after k iterations. Right, every one of these differences in criterion value is going to be larger than the very best difference. This is the minimum. This is the one that achieves the minimum of over all iterations. And now this is essentially the result that we're looking for, because this is what we wanted to kind of provide some control over, the difference between the best after k iterations and the optimal criterion value. So I'm just going to divide by the sum of the ti's. This is less than or equal to r squared plus the sum of the ti squareds times g squared divided by 2 times the sum of the ti's. Oops, I'm sorry. Okay, so this is what we call the basic inequality. Okay, and I'll just repeat once more. I'll sound like a broken record. You know, this maybe transparently is different from what we've done for gradient descent and what we'll do for Newton's method, but in spirit it's very similar. We just start with the assumptions we have, right? And it kind of directs us where to go in some sense. And we try to compare what was happening at the current iteration to the past one. Because the definition of all of our optimization methods, they're local, right? Tells you where to go after you. If you're at a current iterate, you go to the next one according to some recipe. So you just use that along with some set of assumptions you have, like Lipschitzness. And then whatever comparison you have of iteration k versus k minus 1, you iterate or you aggregate, or in some sense you try to make a statement about iteration k globally in terms of where you started. And that's what we've done here. And it's essentially at this point just rearranging to get the result that we want. So this basic inequality, we can actually exactly read off both theorems just from this basic inequality. Right. So let's take ti equals t for all I. Then the right-hand side here is just going to be r squared plus, well, this is the sum of ti squareds from steps I equals 1 through k, but they're all the same, so it's just t squared k g squared divided by 2 times the sum of the ti's. That's just t times k. Right, and if we were to send the number of iterations k to infinity, so let k go to infinity, then this doesn't matter, right? And we're just going to get g squared times t over 2, right? Because we have a common factor of, we have t squared and t. So that's kind of the first fact we proved. And the second fact, or the first fact we claimed, the second fact we claimed, what is that if you took these to be diminishing, then this right-hand side, which is exactly, I'll just rewrite it, this quantity, okay, now you can see exactly why we required those conditions that maybe appeared a bit abstract before. It's so that this thing actually goes to something that's finite, and this thing goes to something that's infinite. Right, so the numerator is going to just approach some constant, and the denominator will approach infinity. So according to our conditions that this, be finite and this be infinite, this just optimal gap goes to 0, which is just to say that in the limit, I'm going to achieve the best criterion value. Okay, let me just pause there and see if there are any questions before we continue. Yeah.
Iterate stuff, why wasn't it a sum of given ones? You only look at the norm.
Sorry, where was this? Are you asking, like, in this step, why don't we get a sum?
Yeah.
So, yeah, I was maybe not verbally that clear about what was going on. So I'm actually not summing these bounds. What I'm doing is I'm applying this same bound to this term. So we said if k is an arbitrary iteration, then I can compare the distance between xk and xk star to what happened in the previous step plus some stuff. I'm applying the same logic to this. So this itself is upper bounded by the distance from xk minus 2 to x star plus tk minus 1 squared times g squared minus the same quantity in terms of k minus 1. And then I'm applying in that first term there the same logic to the distance between xk minus 2 and x star. So I'm just repeating this logic. I guess that's why I was saying iterate, but maybe there's a better word to describe it. So that's why there's no sum. We just end up after all those comparisons with where we were at the first step. Each of these terms came from one of those comparisons. Yeah?
Is there a way to integrate global information into sort of your choice of the degrees? Okay, so let's say there are like finitely many discontinuity points in your gradient, so to speak, or rather, there are countably many. Could you sort of integrate that into the UK?
I'm not really sure, to be honest. So, I mean, I said that somehow this is the right choice for... So let me back up and say there are kind of two applications of the subgradient method. One is kind of classically an optimization. People think it's a very general method. And the other is when you do stochastic subgradient method. So people tend to combine this with something that we'll learn in a couple lectures, but like if the gradient's a sum, or the subgradient's a sum of things, I just take a bunch of those things. And for the second application, that's usually done in applications of ML or statistics, and people don't care about global optimality. So actually they use fixed step sizes, even though I said that we don't really like them. That's the more common thing to do. And they will use fixed step sizes, and then they will just go to until somehow the algorithm's stagnant, and then we'll cut it down by some constant factor. So that's a very common application of the subgradient method, is using a fixed step sizes and not really caring about global optimality. The other one that's the more classic use, which is to use these diminishing step sizes, I mean, actually care about optimizing, let's say, the criterion you write down. There are a bunch of rules that are all about these kind of, that have some kind of growth condition on these fixed step sizes, but I don't know of any that somehow adapt to more specific properties about the function. There's another question up there. Okay. Okay. So we actually have not discussed a convergence rate. We just said that basically we either have suboptimality or we get convergence in the limit. We have not talked about a rate, which is also possible. And the way to derive a convergence rate, well, there's various ways, but one way is actually just to use this same inequality. Okay, and let's just say that somebody asks you for an epsilon suboptimal solution with subgradient method. And we're going to ask how many iterations would that take us. So we know this bound applies. So we're going to just set this equal to epsilon. And we're going to figure out how many iterations we can get away with before this thing is equal to epsilon. Or until this thing's equal to epsilon. And just for the purposes of deriving a convergence rate, we're going to just say, we'll just choose a fixed step size, try to make this equal to epsilon with that fixed step size, and how many iterations would k would that require? So for a fixed step size, this simplifies, as we saw before. Right? We just get g squared times t over 2, because the k's cancel between the two sums for the right term. And for the left term, it's just r squared times 2kt. Right? That's k times t is just this sum. And to make this, let's say, less than or equal to epsilon, it suffices to make each one of these terms less than or equal to epsilon over 2. Right? That will do it. And okay, for this to be less than or equal to epsilon over 2, we see that we have to choose t to be, let's say, epsilon over g squared. Right? If I plug in epsilon over g squared, this term becomes epsilon over 2, so that's what I wanted. That determined my choice of t. And what does that do for this term? Well, to make this term now less than or equal to epsilon over 2, it tells us how many iterations we would have needed. Okay, and when we look at what k is as a function of epsilon, we get r squared times g squared over epsilon squared. So in other words, to get an epsilon suboptimal solution, it suffices to take t to be this value and k to be this value. And what we care about is the dependence on epsilon, which is 1 over epsilon squared. This tells us that the subgradient method converges at this rate 1 over epsilon squared. Okay. So before we discuss the kind of comparison, you might say, well, this was sloppy. You took a fixed step size, and you set these each equal to epsilon over 2. I could have done better. And actually, this is a tight analysis. So you can prove that even with the optimal step size, which has knowledge of f star, the optimal criterion value, so even the very best choice of step size that's kind of unknowable would still attain this rate, 1 over epsilon squared. So if it wasn't a sloppy analysis, you can't do better with a sharp analysis. So what does that look like compared to gradient descent? Well, we actually already kind of talked about this, because this was the convergence rate for gradient descent in the non-convex case to an epsilon stationary point. But I'll just repeat that. If we take epsilon to be, as an example, if we take epsilon to be, let's say 10 to the minus 2, right, or 0.001, then 1 over epsilon means 100 iterations. And 1 over epsilon squared means 10,000. Right, so that is, let's say if the constants in these two rates were somewhat similar, that's a very big difference in terms of how fast we can converge to accurate solutions. Yeah.
So, if our function was completely convex and the differential the subgradient method should reduce the right. So, how would that influence this whole?
So for that, we actually, I mean, not necessarily, because you didn't tell me that the gradient was Lipschitz. So to prove that, we actually use the fact that the gradient is Lipschitz. And that just changes the analysis then, right? Then we don't start with this comparison, we start with the quadratic upper bound. Or is there another question somewhere? Yeah. I'm not good with counting decimals. Thank you. Any other questions or corrections? These are correct, right? 110,000, I think. I could pull up R if you guys wanted me to check that, but okay. So I'm going to just give you an example so you can see, how fast, let's say, something like this is converging compared to gradient descent. So I'm going to take logistic regression. So this is, I can't remember if we've talked about this before, but hopefully it's familiar to you from, previous ML or stat class. So I'm in a classification setting where I have features and I have now class labels. So these yi's are binary, 0, 1. And I'm going to look at doing logistic regression with some kind of regularization. So this is logistic regression loss function. Okay, it actually bears many similarities in some ways to just regression, least squares regression. And we could take its gradient. Well, first of all, I mean, I shouldn't have to ask, but I will anyways. Is this convex? Yes, it's convex. This is linear. And this thing is a log sum of exponentials, which we saw was actually convex. That was one of the examples we highlighted. This thing comes up a lot in classification or multi-class classification. So knowing this function is convex, log sum of exponentials is very useful. So this is convex in beta. And its gradient is exactly this. This bears a lot of similarities to the gradient in least squares regression because this is the inner product between the features and the residuals, yi minus, in this case, its residual is actually a probability vector. So I'm using this notation pi of beta to be e to the xi transpose beta over 1 plus xi transpose beta. So this is the kind of predicted probability according to the logistic model of seeing class 1 if the feature was xi. Okay, so this you could derive just by differentiating that criterion. That's the gradient, just for your reference. So we're going to consider doing logistic regression, so minimizing this over beta with some kind of regularization. And I'm going to choose one form of regularization that's smooth and the other that's non-smooth. So I'm going to apply gradient descent to one and subgradient method to the other. And the kind of natural choices are to use ridge regularization or the lasso. So the squared L2 norm or the L1 norm of beta. Okay, and this lambda is just some fixed tuning parameter for my experiment. And as I said, I'll use gradient descent for ridge and subgradient method for the lasso. And this was an example with 1,000 observations and 20 features. And okay, so step sizes are going to influence what we see here. But I kind of hand-tune the step sizes in each case to be favorable for each method. So we're seeing what should look like the best case behavior for each method if you choose step sizes within what's kind of normal for them. So diminishing for a subgradient method and something small and fixed for gradient descent, and just tune that to get the fastest conversions. So this is a plot of the criterion gap after k iterations. This is a log scale. This is also a log scale. And we can see that we get what looks like a straight line. So this is what we call linear convergence in the optimization lingo, but it's like something to the power of k, where that something is less than 1. This nice linear rate, because this function it's strongly convex on some sub-level set. If we were to cut the function and say, let's look at all the values for which the criterion is less than or equal to what it was at the initial point, it's going to be strongly convex on that sub-level set, and we're going to get this nice linear convergence rate. This is what subgradient method does for us. And I looked at two different choices. One was fixed step sizes, and I chose it to be as big as I could before it started diverging. And the second was these diminishing step sizes. And I chose this again to be kind of favorable. So this one is fixed at 0.001. That's this black line, which we see is just bouncing around some value, which according to our analysis is no more than g squared times t over 2. And this is what I get with diminishing step sizes in red. I get this slow convergence rate compared to what happens in for gradient descent. And just take a look at this, the scales of the y-axes. They're completely different, right? After 200 iterations, I haven't really even come close to achieving a criterion gap that's, 0.01, let's say. And here, after something like 50 or 60 iterations, this is getting close to like numerical tolerance on, in most computing platforms. So you can't really record much smaller numbers reliably. Yeah, question. Yeah, I guess that's probably important. So I generated features here that were standard Gaussian, so it's actually very nicely conditioned. So neither method should have problems with conditioning. And I assume, because I don't remember exactly what I did, but I assume I probably just used random labels, so unrelated to the features. This is not really sensitive to that. It's really a matter of, well, it's kind of two things. One is that we're kind of forced to choose these step sizes when we use the subgradient method, because that's all we know converges. And that plus the fact that we're not always computing gradients makes it converge very slowly. Yeah?
More than one subgradient, it's just random choice.
Yeah, you can pick, I mean, it could be random, like you could actually do something that followed some kind of distribution for randomness, or it could be arbitrary. You could just pick one according to some arbitrary deterministic rule, and either one's fine. The convergence analysis just treated G as something that was a subgradient. Yeah. Well, you hopefully got something out of the last lecture where we talked about subgradients, but we treat it kind of somewhat similar to how we do checking convexity, in the sense that we know how to compute subgradients for like a bunch of basic functions, like norms. We covered the L1 norm last time, so we can compute subgradient in this guy, and other basic functions. And then we have some rules for the subgradient calculus. Like we know how to pass subgradients through more complicated transformations. So here, I guess we could just say, did I have a slide on that? No. So my criterion is the sum of two functions. Subgradients we know decompose over a sum. So it's f plus like the penalty. So subgradient of this, well, I'm just going to take the gradient of f because it's differentiable. And this guy, I can move the lambda out, and this is a norm. So I know how to compute a subgradient of that. But even if this was more complicated, we had some kind of composition rules. I mean, beyond somehow recognizing special cases or doing a literature search, I'm not aware of automatic subgradient calculus, like we have automatic differentiation. I'm not really aware of that being, if that's what you're asking, I wasn't sure.
What if you work with like a local subgradient?
That's a good question. So I think the question is, well, I'm kind of, I guess, imputing the question, but the question I think is, can we define a notion of a subgradient that, say, only achieves this linear lower bound for in some neighborhood? And the function actually maybe could be non-convex or something, and so there could not be a subgradient, but at least it's a subgradient in some neighborhood. So that's actually called a Clark subgradient, after this guy Clark, who has lots of papers on this topic. They have some interesting properties, and you can develop some kind of theory and algorithms around subgradients like this that have these local properties for non-convex functions. The problem is that these tend to be very hard to work with in practice. So it's actually typically kind of hard to characterize what these look like for lots of non-convex functions you might care about. So there's another notion of subgradients that weaken the condition for non-convex functions, and I'm forgetting who they're named after, but yeah, I don't want to write it down because I'm at this point I'm probably just misremembering the name. But if you're interested, you could swing by my office hours. I could try to find it. Okay, all good questions. I think we maybe you can just take a break and then come back and do some examples. A rare treat where we're not rushed. I don't actually have that. I have a few more things to say, but we'll definitely make it in time without rushing. So I wanted to introduce something called Polyak step sizes, which are not something we could ever use in practice, but are the optimal step sizes in some sense if we look at the first step of the subgradient method proof. So remember we had this upper bound, wherever I wrote it down. This was like one of the early steps of the subgradient method proof. Okay, and now you could ask, what is the value of tk that makes this as small as possible? This right-hand side as small as possible. In fact, just this part as small as possible. And that is exactly this value. Okay, this is just a quadratic in tk. So it's not something that we can use in most practical applications because it depends on the optimal criterion value. So it's not really cheating because it doesn't depend on the solution. That would probably, I would say, would be even stronger form of cheating. But this depends on the optimal criterion value. So if we know something about the criterion gap, and in some problems we might, like I'll tell you a problem in the next slide that is an example of one in which we would know that, then we could take these step sizes and in fact you can show that the convergence rate of these step sizes is still 1 over epsilon squared. So this is what I meant when I said that this kind of argument we gave to say that it suffices to take this many iterations to make this bound at most epsilon, that was actually tight because even with somehow these very best choices of step sizes, we get the same rate. Yeah?
So in practice, we do view over these Lipschitz coefficients. Do we could view over as
In practice, we don't. Sorry, say it again. I didn't understand that.
we view over things like L, G,
Yeah.
So here we could view over
Yeah, that's interesting. So you're saying just run this for a bunch of guesses, and yeah. I'm not sure. That may be something that could be effective. I've never seen that. Okay, so here's an example of a problem in which we would know. Oh, there's another question. Yeah.
So could we replace S star with something like a
I don't know. So if we lower bounded f star, then I'm trying to see what we would say about the convergence rate.
potentially could be really large, like TK.
Yeah, if we lower bounded f star, I don't know we'd have a statement about the gap between what the best iterate and f star. We'd have a statement about the gap from the best iterate and our lower bound f star. Potentially, but that also seems like it would suffice. I'm just not sure I can do it in my head to figure out what that would break. Yeah, both good questions. I'm not sure.
TK is large, then it could diverge a bit. So you got to avoid this divergence.
Sure. Yeah. I mean, in some sense, it may be a balancing act, but yeah, if TK is, if somehow these, let's say, if I lower bound f star, if these grew, they weren't even constant, then we know that wouldn't work. Okay, so people usually think this is just not realistic, and then there's a nice example. Actually, I think both gives you a sense of a problem in which f star is known, even though we don't know the solution, and also it's a very interesting application of the subgradient method in terms of what comes out. So we're going to see that the subgradient method actually reproduces a very natural algorithm. And so this is the problem. Let's suppose it's actually a feasibility problem. I gave you a bunch of closed convex sets, m of them, and I told you I just wanted you to find a point in their intersection. Let's assume the intersection is not empty. Okay, so this might be, when we talk about constraint optimization in more detail later, when we talk about second-order methods, for some of the second-order methods that we talk about, you need a feasible point to begin. So I can't even begin running, let's say, a standard application of Newton's method. I can't even begin to run Newton's method if I don't have a feasible point, if I have some constraints. So you need to find a feasible point somehow. And there are better ways, in some sense, to do to solve to find feasibility points. But we can just ask, what would the subgradient method do? And we're going to pose the problem this way. And we'll see it actually, it reproduces a very natural algorithm. So when I said better, I meant maybe more efficient, but at least in terms of intuition, this gives us something quite nice. So we're going to actually say that the problem is to minimize the maximum distance between our optimization variable x in each of those sets. So let's define f of I to be the distance between x and ci. This is convex. We've done this as an example in the past. This is a convex function of x as long as ci is convex set. And a max of convex functions is convex, so this whole criterion is convex. Okay, so we're going to now ask, what would the subgradient method do to minimize this function f? And if I told you the intersection was not empty, then that means that f star is 0. Right? If you knew that there was a feasible point, then that means that what we're looking for is something whose criterion value is 0. It lies in each one of the sets, so the distance to each set is 0. And we're going to actually now apply the subgradient method with these step sizes, where I plug in 0 for f star. So we're going to have to do a couple of calculations to get the subgradient method to work, at least to see what its iterations are. So let's think about each one of these sets f of xi, which is the minimum, let's say, over all y in the set C, distance between x and y. This was the distance function. The ith set. Okay, so it looks something like this. Like this might be x. And this might be we'll call this the projection onto ci of x. It is the value of y that minimizes the distance between x and y over all points in the set. Okay, so last time we actually proved that this function, or we didn't prove, it was in the slides and it was the last example, and I said that the proof was we could skip. So you'll have to just trust me that wasn't made up. And we actually, let's say, claimed in the slides last time that the gradient, this function was differentiable, first of all, when x lies outside the set, and its gradient was exactly this thing. So if I were to take the vector that points from the projection of my point onto the set and the point itself, and I were to normalize it, that's the gradient. That's what this thing is, this thing. So now we know how to compute gradients of each one of these individual functions, fi, but I have to compute a subgradient of f. Right? That's my task for the subgradient method. So we're going to apply the subgradient rule for a maximum of functions, which we learned last time. So if I were to look at a maximum of functions, and I were to compute the subgradient, then the rule was I take all of the functions fi that achieve the max, so all i's such that fi of x is equal to f of x. I take their subgradients, I collect them, and I take the convex hull. Okay, and in our case, this is actually a singleton. It just has one element, and that's this. right? Because our FIs are differentiable, so their subdifferential has just one element, and that's the gradient. There's just one subgradient, that's the gradient. So this is the rule for all of the subgradients, but in fact, if I just asked you for a subgradient, right, which that's all we need for the subgradient method is knowledge of how to compute a subgradient, just a single one, then you could just pick any I that achieved the max and take one of its subgradients. So for us, what does that mean? I can pick any set that my point is farthest away from, right? Maybe there's just one, but maybe there are some ties. So suppose I have different sets. Maybe x was equally far from two of my sets, Ci and Cj. I could just pick either one, doesn't matter. And I could take either one of their gradients. And that would be a valid subgradient of my function f, right? Because it would just be something in here. So we're going to actually use that rule for the subgradient method. So just rephrased, putting this kind of logic in the context of our problem, if we just take some set Ci that's currently farthest away from x, and we take Gi to be equal to the gradient of that distance function, which is just x minus its projection over the norm of its projection onto the set Ci, then that thing is a valid subgradient for our entire criterion. And so now we can ask, what would the subgradient method do? Right, the subgradient method would actually do this. So what would this look like if I took, let's say, x was farthest, let's say x k minus 1 was farthest from Ci. So I found the set that it was farthest from. And I now used as my choice of subgradient x minus the projection, I should say xk minus 1, divided by its norm. Okay, and I'm going to use for tk the Polyak step size. Okay, so for tk, I'm going to do f of xk minus 1 minus f star, and that was 0 for us, right? Because we know that the sets have non-empty intersection, divided by the norm of this subgradient squared, but this subgradient has just norm 1. Right? This thing has norm 1. So that's my update. Okay, and now we see something else that's quite interesting. If I told you that xk minus 1 was farthest from Ci, then the criterion value is exactly equal to the distance between xk minus 1 and Ci, which is exactly this, right? If I picked out the Ci that was farthest from x, then the criterion value is exactly this distance. It's the maximum distance to all the sets, and Ci I'm telling you was the max. So that means that these things, this criterion value and this distance cancel, they're the same. And we can see the subgradient method actually exactly gives us as the update, just project onto Ci. That's the whole update. And remembering that Ci was the farthest, this is a form of alternating projections, where at every step we're projecting onto the farthest away set. Right? So if Ci is the farthest, we project here. Next iteration is another set that's farthest, we project there, etc. So just for two sets, so von Neumann has a famous paper in 1950 that proposes this for two sets. For two sets, the other one is always the farthest one away. So I'm just literally alternating between, like, say, set C1 and C2. For multiple sets, I think it was this other guy, his name is Halperin, in the 60s, who basically proposed this algorithm, project to the farthest set away. And what's interesting is that this is an algorithm that you might have thought of from first principles, right? If you just tried to find a point in the intersection of sets, you might have thought of doing some kind of alternating projections. So it's very natural. And on top of that, we get kind of for free the fact that we know that this converges at the rate 1 over epsilon squared. So if I tell you I want something that's epsilon close to every set in L2 distance, I want you to find a point that's, has a distance of epsilon to every set, then I need 1 over epsilon squared iterations of this. If you try to approach that from first principles and prove that maybe geometrically that you had that rate, it would have actually been pretty non-obvious how to do so. Okay, if there's interest, I may return to alternating projections at the end of the semester. I think it's pretty interesting, and there's actually a lot of other algorithms that improve on even this alternating projections algorithm, but that are still alternating in flavor. So if there's interest, I may do an advanced lecture on that. So the last thing I wanted to say, I think, a couple things more, is what to do with constraints. And what we're going to talk about today for subgradient method and next time for gradient descent, we can handle some constraints. And when we talk about second order methods, we'll describe a way to handle much more general constraints. And the constraints we can handle at this point are constraints that we know how to project onto. So if I wanted you to minimize a function over a constraint set C, if you know how to project onto C, then you can just apply the projected subgradient method. So you take the usual subgradient step. Okay, this will likely put you outside of the constraint set, and so you just project back onto the constraint set. You just find the closest point, let's say this is exactly this, an L2 distance in the constraint set to where your update took you. And in fact, the projected gradient descent works as well. And we'll cover that more next time because it's a special case of proximal gradient, which we'll talk about next time. But assuming that you can do this projection, you have the same results. So with the same step size choices, you get the same rate. So it's worth just pausing and asking, what kind of sets are easy to project onto. And there actually may be more than you would expect. And the best thing to do is just to search the literature if you have a set that you're looking to project onto, because somebody may have a fast algorithm for it. But here are some things that are, let's say, some simple things that we can do. Like, for example, any affine space, any linear space, so a solution to a linear system, the non-negative orthon, this one's very easy. We would just take any vector and truncate the negative entries to 0. Projecting onto norm balls, so projection onto the 2-norm ball, we just have to rescale the vector by its norm, 2-norm. Projection onto the 1-norm and the infinity norm are different. This one is very easy. So this one, if I project onto the infinity norm ball, I just have to, let's suppose I had some entry that was bigger than 1, and I'm projecting onto the infinity norm ball of radius 1. I just would move that, that's kind of the picture. I just would move that to have 1 in each entry. Projection onto the 1-norm ball is actually not nearly as simple, but there are some papers that show you can do this in nearly linear time. Or maybe it's actually exactly linear time if you use a clever... So it's definitely possible in n log n, and I think it may even be linear. So this is an example of something you should search the literature for. If you want to project onto the L1 ball, there is an efficient algorithm. There are several papers on that. Other polyhedra and simple cones, like, for example, the space of positive semi-definite matrices we can project onto. That's an example of a cone. There are lots of other kind of simple examples. So on the flip side, it's important to give a warning, which is that there are lots of things we can project onto, but it's really because these things are tractable. We can write down exact algorithms for what the projections look like. And if you just move a little bit away from this, you can end up at a set that you don't know how to project onto. So a good example of that is a polyhedron. So you might think, well, look, this is a linear space. This is like a very simple polyhedron. What happens if I just have an arbitrary polyhedron, intersection of half spaces? So projecting onto this enclosed form is not possible. And in fact, this is as hard in some sense as a generic QP, quadratic program. So it's not easy. It's not something you like to do as a subroutine typically. You typically want to do projections here, as subroutine that are quite cheap. And those are examples that look like this, and others where the projection is almost linear in the number of variables in terms of its cost. So yeah, projected gradient descent works as well. We'll talk about that more next time. And later, when we talk about second-order methods, we'll talk about how to handle constraints where we don't know how to project or we don't want to project. It's a very different way of handling them. So the last thing I wanted to mention is a notion of optimality, just like we had with gradient descent. So just to recap, we showed that if we have, let's say, functions that are convex in Lipschitz, then the subgradient method converges at this rate 1 over epsilon squared. That's pretty slow. That's not a very fast rate. It means that we have to spend a lot of iterations kind of fine-tuning in terms of accuracy. And thanks to Nesterov again, we have a lower bound on how well we should expect to do kind of over a class of methods that use similar amounts of information. So I'm calling this non-smooth first-order methods. These are methods that at every iteration, they update the current iterate somewhere in the span of the first iterate, so where we began, plus the span of the subgradients we've seen so far. So if we replace these subgradients with gradients, that was a first-order method. And now, we're looking at a case where the function is not differentiable, so the most natural thing to do is replace this with subgradients. And what I mean by weak oracle is that you don't have choice of the subgradients. So somebody is just giving you a subgradient. You don't get to pick which one. Okay, it's maybe more, it's more pessimistic, but in some sense it might be more realistic because in some settings it might be difficult to compute all the subgradients, right? You just know how to compute one. So this theorem of Nesterov, very nice theorem, says that essentially for any algorithm in this problem class, so these non-smooth first-order methods, there is an instantiation of a function f that is Lipschitz, and there's convex in Lipschitz, such that your algorithm, after k iterations, will have a criterion gap that's lower bounded by something over square root of k. Okay, so the convergence rate is 1 over the square root of k. That is actually exactly the same as this, 1 over epsilon squared. Right? To get an epsilon suboptimal solution, we need to take on the order of 1 over epsilon squared iterations. So in other words, we can't do better. This is the very best we can do. So, as slow as that is, there is no other method that uses the same amount of information as subgradient method and does better uniformly across the board. We have to use more information in some way. So what we're going to do next time is, instead of trying to minimize generic convex functions that aren't smooth, which we see is very hard, we're going to talk about functions that have more structure. And there's two reasons that's appealing. The first is that actually many times in practice, like for example, this problem, if I add the logistic regression loss to the one norm, the result is not smooth because the one norm is not smooth. It's not differentiable at 0. But that's actually a fairly simple non-smooth function. And I can think about this as actually, rather than just being one big non-smooth function, the sum of a smooth function with a simple non-smooth function. And if I think about problems of that form, okay, let's say g plus h, where this can be complicated, but it's convex and smooth, and this is allowed to be non-smooth but simple in some sense, turns out we can do much better than the subgradient method. And it's also appealing because a lot of problems that we run into in practice are of this form. So we'll see that actually we can get back the same rate as gradient descent for problems of this form. And even better, if we accelerate the method, we can get back actually an even faster rate. So we'll talk about that on Monday, and I will see you guys then.